Section 18.9, Gauss's law. So Gauss's law is an important general result that allows people to solve for electric fields of both the ones that we already looked at, derive those equations, and then any number of arrangements of charges. So to derive it, we're going to start with one that we've already seen, the point charge. So the electric field of a point charge, we said, is kq over r squared. If we instead write that in terms of epsilon naught, our permittivity of free space, right? We could write the k, remember, is equal to 1 over 4 pi epsilon naught. And that allows us to get it into the common form of it. Now, 4 pi r squared, that's something that you may have seen in math class before. Maybe it's been a while. That's the surface area of a sphere. So if we have a point charge and we imagine having a spherical, it's called Gaussian or Gaussian surface, we draw a sphere outside of the point charge surrounding it. And we can say the area of that sphere, of all of that surface surrounding the point charge, is 4 pi r squared. Well, knowing that, then we can plug in that is our area. So we get that the electric field is the charge divided by the area divided by epsilon naught. If we then multiply the area to the other side, we get Gauss's law for a point charge, that the electric field times the area is equal to the amount of charge enclosed by our spherical Gaussian surface divided by epsilon naught. And this electric field times area is an important concept. It's known as the electric flux. And so this is true if the electric field is exactly piercing the area, if it's going straight through it in the same direction as the normal to the surface, that you can calculate the electric flux with the electric field times the area. And that's what happens with a point charge, right? That's why we use the sphere shape of the Gaussian surface around the point charge, because then the electric field lines are going to pierce the sphere and be exactly perpendicular to that surface that we've drawn. We will see some cases where maybe it doesn't perfectly pierce the surface and go perpendicular through the surface. In that case, our electric flux, which by the way is the Greek letter phi or phi, this is the capital version of it with an E subscript, because we will see magnetic flux as well. So this is electric flux. So for it, if it's not exactly perpendicular, then we have the electric field times the cosine of the angle between the electric field and the normal to the surface. So let's write that out in words. Angle between electric field and normal to Gaussian surface. So that's what's shown here, where we have the normal is pointing straight out from the area segment and the electric field is pointing off at some angle, and E times cosine of phi then allows us to find the amount of electric field that's just going straight through the surface. So it's a slightly longer version, but you can see, hopefully, that if the electric field is going straight through the surface, perpendicularly through it, then it is at an angle of 0 degrees. And if you have an angle of 0 degrees with the cosine of 0 is 1. And so when you are going straight through, the simplified version is that the electric flux is just the electric field times the area. All right, so we're going to put this more detailed version back into that Gauss's law that we derived for the point charge. So keeping this in mind, we can find a formal definition of Gauss's law that the electric flux through any Gaussian surface is equal to the net charge enclosed in that surface divided by the permittivity of free space epsilon naught. So on the left here, we have our electric flux, which we could write again as the phi sub E. I like to think of it as a little TIE fighter, if you're a Star Wars fan. And then Q, notice this is a capital Q, so it's not a lowercase q like our others have been. And that's because this is specifically focusing on the charge enclosed. This is sometimes even written as Q sub E and C, because we want this enclosed charge. What does that mean? Well, in some cases, we can draw our Gaussian surface because the Gaussian surface is whatever we want to pick. We get to choose it, but there are some that are easier to work with than others. And that surface, in some cases, will just enclose all the charge. Cool. In other cases, it will enclose none of the charge. Also cool. And then there will be a few cases where it encloses part of the charge. And so with this, we're going to need to figure out how to describe how much of the charge is enclosed. So one way we can do that, if we're working with a three-dimensional Gaussian surface, as is shown here, is we can work with the volume charge density and multiply that times the volume. So volume charge density multiplied by the volume V of our Gaussian surface, and that can tell us how much charge is enclosed, right? Where the volume charge density could be, for instance, the total volume and the total charge. Divided by, yeah, so the total charge divided by the total volume. But then the key is, instead of multiplying by the total volume, which would just cancel it out, in some cases that might be true, we're just going to multiply by the enclosed volume of the Gaussian surface. So however we drew it, the Gaussian surface is made up. It doesn't actually exist, but it helps us mathematically to approach these problems. All right, so that's a bit of an aside there. If we're thinking about electric flux, it's electric field times area, and the units are going to reflect that. Remember, our electric field units are newtons per coulomb, and our area units are meters squared. So the overall units of electric flux are newtons meters squared per coulomb. A little bit lengthy, but that works just fine. All right, so now that we've seen this, let's check out an example. So the electric field of a charged thin spherical shell. A positive charge is spread uniformly over a shell. Find the magnitude of the electric field at any point A outside the shell and B inside the shell. All right, so as we're approaching this, for A and B, we're going to need two different Gaussian surfaces. Now we want our Gaussian surfaces to match the object of interest. So here, since we have a spherical shell, we're going to want a spherical Gaussian surface. In case A, we're looking outside the shell, so we're going to draw our Gaussian sphere outside of it. That's what's shown with this Gaussian surface S. It's the blue bubble outside of it. It's not actually there, but it's a helpful way to approach this and think about it. Right, and then in part B, we want to find it inside, so that's where we're going to still draw a sphere, but it's now going to be at a smaller radius. It's going to be within the shell. So for each of these, we want to look at our Gauss's law. Let's take a look at how this plays out. So Gauss's law says that the electric flux is equal to the sum of the electric field times the cosine of the angle between the electric field and the normal times the area element. And conveniently here, the electric field lines are piercing the area of the surface. That's why we draw the surface as a sphere. So the angle is always going to be 0. And the electric field will always be in the same direction as the area. So the electric field is uniform anywhere on this surface. We can pull that outside of the summation. And if we sum up all of the areas, we would just get the area of a sphere. As mentioned before, that's 4 pi r squared. So if we're dealing with a Gaussian sphere, This is going to be our area equation. That gives us then the left side of Gauss's law. We know that the right side is the amount of charge enclosed divided by epsilon naught. Well, how much charge is enclosed within the shell? Well, the amount of charge enclosed within the shell, or enclosed within the Gaussian surface, is however much charge is on that shell, right? So if we go back to the previous slide, it just said there's some positive charge. It's going to be whatever that positive charge is. So outside the shell, it encloses all of the charge, where we can put in that the total amount of charge enclosed is just little q, all of it. And so if we divide the 4 pi r squared to the right side, we get that the electric field outside the shell looks like q over 4 pi r squared epsilon naught. What about inside? If we're inside, notice the same rule will apply of that the electric field is going to be in the same direction as the area, so we can use the same result as before, but how much charge is enclosed? Well, now our Gaussian surface, that bubble doesn't have any charge inside of it. So because the amount of charge enclosed is 0, the electric field is also 0 inside the shell. So when there's this open space of air here, the electric field is 0 anywhere inside. Doesn't matter if you're right next to the thin spherical bit or really in the very middle, the electric field will have to be 0. What does this mean? Well, if we look at this, we could rewrite this as kq over r squared. We've basically re-derived the electric field of a point charge. So if you are outside a thin spherical shell, it just looks like a point charge. If you're inside a thin spherical shell, it looks like you're inside a conductor. There's no electric field there. So this is one example of how we can use Gauss's law to derive results for the electric field. You'll get to look at one more really solid example with a solid insulator, at how the electric field will vary as you move through the insulator. So that will be really interesting. One more thing to wrap this up is, how do we use Gauss's law? A reasoning strategy here. So first off, we're going to usually draw the Gaussian surface to take advantage of the symmetry, which in most cases will either be a sphere or a cylinder. So if you have a point charge, you're going to draw a sphere. We use the cylinder for if we have a parallel plate capacitor, because then we can put the circular side of one end of the cylinder in one of the plates. The rounded sides of the cylinder will be traveling in the same direction as the electric field, and then there's a nice cap that is in the midst of the electric field. And so that's a nice way to test the electric field of a parallel plate capacitor, for instance. So cylinder or sphere, focusing on finding what is symmetric. We're going to also check where the electric flux through the surfaces is 0. So if there is no electric field lines through it, like in 1, there's no electric field lines there, then the flux is 0. Also in 2, because the electric field lines, surface 2, the curved sides of it, the electric field lines are all going alongside of it, they are not piercing the surface. So case 2 is another one where the electric flux is 0. The only non-zero flux in this drawing of the cylinder in a parallel plate capacitor is the flux through surface 3, where the electric field is piercing right through that area of end cap 3. That simplifies our problem quite a bit. Then we can calculate the desired quantity. Maybe it's asking for the electric field, maybe the area, maybe the amount of charge, with any of the surfaces of non-zero flux, right? So we'll pay attention to surface 3, and from that we'll be able to calculate what we need to get. And we are always going to be trying to draw our surface so that the electric field is piercing the surface. It's in the same direction as the normal, where the angle between the electric field and the normal is 0. So that will be most of them. It simplifies things out quite a bit. All right, so I know this was a long chapter. We packed quite a bit in, but thanks for writing it out. And If you have questions, please do ask. I would love to discuss things further, either in the discussion boards or in office hours or in class. So, see you soon and stay in touch. Hope you are still charged up about this.